The entries of a vector in Rn depend on the basis that you've chosen to represent that vector in. Here is a simple picture of a vector in R2. If, for example, we choose standard basis, this vector x would be 0 and -2, which means 0 bunches of E1 minus 2 bunches of E2. Now, when we change the basis for the space we're in, it changes the entries of the vector, not its location. So, for example, if we wanted to use a different basis for R2, then the vector that we've got still remains the same. What will change is the set of instructions for how to get to this vector. So let's call this vector V1, and we'll call this vector here V2. The vector x can be represented as -1 bunches of V1 and 1 bunch of V2. So that's going to be -1 bunches of 1, 1 and 1 bunch of this vector. This gets you to 0 and -2. So we would go -1 in this direction and +1 in this direction, and that would take us to the vector that we want. There's an algebraic relationship that connects these two different bases. If we use the definition of matrix vector product, we're going to see that this is the matrix V1, V2 times this vector that holds the weights. We're going to call this thing P, and this thing here we will call X with this subscript B. So this is the relationship between the entries when we switch between these different bases. Now, in general, if we have some vector u, we can write it like this. And because this matrix P holds basis vectors, this matrix can be inverted. We could put that inverse on the other side and isolate for this coordinate vector. This thing holds basis vectors, and this is what's called the coordinate vector in the new basis. Switching bases connects entries of a vector in an algebraic way. In the context of a linear transformation, we are going to see that the entries of a matrix will also change in the same way. For us, we're just going to focus from going from the same vector space to the same vector space. We will see that the entries of A also change in a similar way. The changing basis idea that we just went through is going to be the foundation for what it is that we do. So let's stick with R2. We're going to take a transformation that goes from R2 to R2. So let's take this particular one, and we'll talk about changing basis. And the basis we will use is the same one we've been using up to now. So 1, 1, 1 with a -1 here. If we switch from standard basis to another basis, it's always possible for us to reorganize this equation and connect the two representations in this way. So I'm going to draw a little diagram. If I'm in standard basis, I can represent the vector, let's just say x. If I want to switch to a different basis, the entries or the name of the vector just changes, but it's the same location. From this conversion, if you know the standard basis form and you want to go this way, you have to multiply by a P inverse. Now, if we are in standard basis and we know that there's a linear transformation, that linear transformation changes our vector from x into ax. I could have also have converted that answer ax into the new basis. There's going to be some matrix here. So I'm going to call it matrix M. If I have a vector u and I want to figure out what its name is in this other basis, I know that this connection exists. Now, really, it doesn't matter what that u is. Whatever I put on this side has to go on that side. Take this ax, put it in here. It's got to live on the other side. Now, there are some very handy matrix properties that say you can switch the order of these brackets. So I could write it as P inverse times A multiplied with this vector. Wherever I have this vector x, I'm allowed to use this conversion formula. If I use matrix multiplication properties, I'm allowed to group these three things. If I start with x, and I turn it to ax, in standard basis, I've taken some matrix A and multiply. If I translate languages to the B basis, I have just shown this matrix will perform the same action in this new basis. So this matrix M, P inverse AP, is what we call the representation of A in our new basis. Now, in the context of our example, M is P inverse AP. P is a matrix that's formed from our basis vectors. So our basis vectors looked like this, very straightforward. It's also very straightforward to invert a 2 by 2 matrix. There's a simple formula. You can use row reduction, whatever you'd like. Our original matrix in the standard basis was given by that. So if I sit there and I compute this product, what you'll find is that if we put them in this order, you can either multiply left to right or right to left. You can take a moment and you'll figure out that this works out to the following. That gives us something neat. It's very easy to see what this matrix does in this new basis. So in this B basis, the transformation acts to stretch by 2 in the V1 direction because of this entry there, and then it flips in the V2 direction because of this entry here. It was not obvious from the standard basis what that transformation was going to do. Making a switch of basis clarified for us what it is that this matrix does. Now that's going to turn out to be very important. We are going to define something called similar matrices. Similar matrices represent the algebraic connection between matrices when we switch bases. So if these are n by n matrices, we will say that these two matrices A and M are similar matrices if there exists invertible n by n matrix so that A is PM P inverse, or if you wanted to think of it, just a revision of this formula here. Now note, if I have this relationship here, if I wanted to, I could say, hey, this matrix G is P inverse. G inverse would be P inverse. Inverse would just be P. This would be G, A, G inverse. And that means if A is similar to M, it also implies that M is similar to A. Now remember, similar matrices are just a way to represent the algebra connection between matrix entries when we switch bases. Why do we call it similar? What's similar about them? Similar matrices are not equal. The entries of similar matrices are different, so the matrices are not equal. They are also not equivalent. Now, equivalent is this word that means they have the same solution set. So for example, AX equals 0 and MX equals 0 are going to have different solution sets. So they're not equivalent either. They're not equal, they're not equivalent. Well, then what is similar about them? What do you get that is the same? Well, you do in fact get many similar features. If two matrices are similar and we say A is PM P inverse, or if you wanted to reorganize this as P inverse AP, then when I say the determinant of A, that's like saying the determinant of this product, PM P inverse. The determinant of a product is the product of determinants. You also know that when you take a matrix and its inverse, they multiply to give you the identity. If you take the determinant of both sides, you'll get this property, and the determinant of the identity matrix is 1. So anytime you see determinant P times determinant P inverse, they will just give you a 1. So this has to be equal to the determinant of M. So if two matrices are similar, and they're square by definition, they have the same determinant. Now this means if A is an invertible matrix, M has to be invertible as well. If one is invertible, the other one is invertible. Remember that when we calculate eigenvalues, we have to take this equation, it's called a characteristic equation, and we have to set this equal to 0 and solve for lambda. Remember that when you have the identity matrix, you can always write it as P times P inverse. Now, at the same time, you are always allowed to multiply the identity matrix anywhere, and it won't change the value. So I'm going to jam an identity matrix in here. Now remember, all of these matrices are square, so I don't really have to worry about the dimensions. There's also a property of scalars. If you want to put the lambda inside, you could do this. Everything in this equation has a P multiplying on the left, So I'm going to factor out that P. And then when I look at what's in the bracket, everything in the bracket has a P inverse multiplying on the right. So I'm going to factor out that P inverse. And now I'm in exactly the same spot that I was in earlier. The determinant of a product is the product of determinants. And like we mentioned before, anytime you see the determinant of a matrix times the determinant of its inverse, it just gives you a 1. The determinant of A minus lambda I is equal to the determinant of M minus lambda I. That means they have the same characteristic equation. Determinant A minus lambda I is 0 is going to be exactly the same as determinant M minus lambda I is 0. Similar matrices have the same eigenvalues. Now remember, we said similar matrices are not the same. They're not equivalent, but they do have a lot of things in common. This is a huge similarity about them. Now in the example I was working on, here's the matrix, and if you just want to verify this, calculate the determinant of A minus lambda I, you would form this matrix. What you would find is that lambda would be 2 or -1. Now we found that we were similar to this other matrix. And if you just want to verify it, you'd go 2 minus lambda, 0, 0, -1 minus lambda, and you want to set that equal to 0. And so the characteristic equation would just be this. And so lambda would be 2 or -1. Now there's a really important note here. If you have a diagonal matrix, the eigenvalues of either a diagonal or even a triangular matrix, so the eigenvalues of that matrix are just the diagonal entries. So that's really handy. Now, circling back to this is a very key idea. Similar matrices represent the same transformation, just in 2 different languages. So the matrix stretches by the same amount, but there's a big difference. If we were to take that matrix A and compute the eigenvectors, lambda is 2, this would produce an eigenvector of 1, 1. If we were to compute the lambda is -1, this would produce an eigenvector 1, -1. But if I were to take that matrix 2, 0, 0, -1, compute the eigenvalues, I would find that they would be different. And that's part of the catch here. Similar matrices have the same eigenvalues, but they have different eigenvectors. But that's okay. This makes sense. And you might say, well, why? Why does it make sense? Remember, similar matrices have to do with switching basis. When you switch basis, you switch the name of the special vectors. You switch the name of the eigenvectors. So if A is similar to M, and if A has eigenvector u with lambda, so AU equals lambda u, you can see that when we do the similarity, there's going to be a well-defined relationship between them. If these two are similar, when I put this in, I'll have PM P inverse times u is lambda u. I'll have PM times P inverse u is lambda u. I'll have M P inverse u, and because this is invertible, I can hit both sides with the inverse on the left. And when I do that, I can play some further games here, pull this inside. So if A has an eigenvector value pair that looks like this, lambda and u, that means M has an eigenvector value pair, lambda with P inverse of u. In the same way that the vectors change names with the basis change, so do the eigenvectors. In our example here, remember that M was P inverse AP, so that means A was PM P inverse. So M had eigenvector 1, 0 for lambda is 2. That means A should have this eigenvector, P inverse times E1. P inverse was given like this, and what we will find is a half 1, 1, and that's exactly the eigenvector relationship that we're supposed to get. Similar matrices are just the representation of a matrix in a new basis. They have the same eigenvalues, they have the same determinant, but they have different eigenvectors, and that makes sense because you changed basis. So now our goal is going to be, can we find a basis that makes some matrix A as simple looking as possible? And that's what we're going to see in the next video.